We have discussed till now what is specific heat of a gas. So I told you that we will be discussing after this that what is the specific heat of a solid and a gas we have discussed, and I told you that the specific heat for gases there are two values: constant pressure and constant volume specific heat. So after this, I will discuss the relation between this Cp and Cv, and that is the Mayer's formula. Cp minus Cv is equal to R, which is the gas constant. So we have also discussed that there are two types of gas constant: universal, which is same for every gas, for an ideal gas, and the characteristic gas constant, that is universal gas constant divided by the molar mass of the gas, which is different for every gas. So I also told you in that uh, discussion that first of all we will discuss the first law of thermodynamics, then we will discuss the Mayer's formula. So I am giving you a brief description of first law of thermodynamics for just to prove this, that is what is first law of thermodynamics. In detail this will be discussed again. So first law, let me discuss first law of thermodynamics. Suppose we have this system and some heat is given to the system. As a result of this, the system is doing W amount of work. This is the work done by the system. So heat going into the system is taken as positive. Work done by the system is taken as positive. Now what does this mean? Let me explain this with the help of this piston cylinder example. This is the system. The gas contained inside this is taken as the system. This is a system boundary, fixed boundary and the movable boundary. So if you give heat to this system, that means heat is given to the ideal gas that is contained. Ideal gas we are taking. We assume practically the gases which are contained in the cylinder to be ideal. So as a result, the energy of the molecules of the gases will increase, and we take into account the energy like kinetic energy, vibration energy, rotational energy, magnetic energy. There are so more, many types of energies, potential energy. So their energy increase. So what happens? The number of collisions on the wall, they are also increasing every side of this. And this is the movable side, so I am showing it here. As a result, the piston will try to move out. If it is not restricted to move, if we do not restrict it from moving, it will move like this, in this direction. On this side, the atmospheric pressure is preventing it to slide out. So the pressure inside is increases as a result of the heat supplied to this. So heat supplied is positive. Now the system is moving out. It means the system is doing work on the surroundings. Expansion work is positive work. This is system expansion, positive work, and we show it on the property diagram like this. This is the pressure, volume is increasing as a result of the pressure. So this work is taken as positive work, and if you compress this, work is taken as negative, and if the heat is taken out from the system, then it is taken as negative heat. I will show it separately. Work done on it, compression work is negative. Heat going out of this is negative. So what results here is, you give Q heat to this energy, as a result it is doing W amount of work. So this is always greater than equal to W. Now equal to stands for thermodynamic cycle, which we will be discussing also. What is this? For a cycle. But for an individual process, Q is greater than W. That means you are giving some energy, some part of it is system is doing work. Where is the rest going? The best example of this is rub your hands like this. Okay, and what you are doing is you are doing the work. Okay, that work is converted into energy. The reverse of this is also possible, which happens in our daily life, like in case of vehicles. You are putting in the fuel in the form of chemical energy that is converted into mechanical energy, or chemical energy that is converted finally into work, which is mechanical energy. So the efficiency of this vehicles which we are using, that is merely 32% or even less, around 30%. So it means that if you put in 100 joule of energy, only 30 joule of is available to you in the form of work, 130. So where is the difference of 70 joule going? This is the question. This answer is provided by the first law of thermodynamics, that the difference Q minus W, because this is the law of energy conservation. That energy can neither be created nor be destroyed, only its form can be changed. So what happens here is the difference Q minus W, this is stored in the system in the form of change in internal energy. This is called internal energy. Okay. So this is the first law of thermodynamics in brief. Now, let us come back to our topic, which we were discussing. The Mayer's formula we have to discuss right now. That is the relation between Cp and Cv. So the Mayer's formula, we are discussing Cp minus Cv equal to R for 1 mole of the gas. What is Cp? Specific heat of the gas at constant pressure, specific heat of the gas at constant volume. This is the gas constant. Now you know that specific heat is defined as Q over m delta T, mass of the system. Delta T is the temperature change, Q is the heat interactions. So C is equal to Q for m is equal to 1 kilogram, delta T equal to 1 degree Celsius or 1 degree Kelvin. So this is the specific heat, as you know, is defined as the heat required, heat interaction of the system with the surroundings is required so as to change the mass of 1 kilogram of the substance by 1 degree Celsius. That is, if you want to increase the temperature by 1 degree Celsius, you have to supply the heat. If you have to decrease it, like in case of formation of ice, you have to take out the heat from the substance. So in this diagram, I have shown the two types of processes. This is the system, piston containing a cylinder in both of them. And on this, we have put some weights so that this does not move out, whereas in this case, it is free to move out. There is no friction. So the gas contained in this is ideal gas. So we have to supply the heat in both the cases so that the temperature of this 1 kilogram of gas in every case increases by 1 degree Celsius. So suppose I supply this dq heat, and in this what is constant? Here the volume is constant, dq at constant volume, and here I will take pressure as constant. Why does this happen? As you can see here, when you supply the heat energy from this, what is the energy is doing? This is increasing the internal energy of the gas molecules or the atoms, and as a result their energy is increasing. The gas will try to push the piston in the outward direction, but this weight stops the piston from moving. That's why this volume is fixed, so it is constant volume process. The pressure is increasing in constant volume, but volume is constant. So here you can say that the work done due to expansion of the system, P dV is equal to 0, as dV is 0, change in volume is 0. So P dV dW, work done by the system, is 0. And here, as you supply the energy of the gas increases. As a result, it pushes the piston in the outward direction. And as the piston moves, it keeps on moving until the pressure here again attains the initial value. The system again comes to equilibrium. So this is called constant pressure process because the pressure is maintained constant. System will keep on moving until the pressure again becomes constant. Okay, means the equilibrium is attained. So the pressure here is constant, that is change in pressure is 0. So we have to prove the relation we have mentioned here. These are the two types of the systems. Now you know that according to first law of thermodynamics, dq is du plus dw. For a constant volume process, dqv is the heat supplied equal to du plus dw is 0 equal to du. And we know that dqv is equal to cv into dt for mass equal to 1 kilogram equal to du. The ideal gases always follow this. For them, Cv is equal to du by dt. This is a function of internal energy is a function of temperature only, and Cv is the rate of change of internal energy with respect to temperature. So this we can write down for the constant volume system by taking 1 kilogram mass, or you can say 1 mole of the system. Now what here is happening? Whole of the energy in this case is used in increasing the temperature of this system by 1 degree Celsius. The system does not have to do work against the surroundings in expansion. And what here is happening? The energy supplied at constant pressure is used up in increasing the temperature by 1 degree Celsius plus doing work against the external, the expansion of the system against the surroundings. So it is used in two ways. So you can say that here for increasing the temperature by 1 degree Celsius, the heat supplied will be more. dQp will be more than dQv for delta T to be 1 degree Celsius or 1 degree Kelvin. So we can write that first law of thermodynamics, dQ is du plus dW. dW is P dV. dQp is equal to this. And dQp is for 1 mole or 1 kilogram as Cp dt. And I can write from here du is Cv dt, Cv dt plus P dV. And from this we can write that Cp minus Cv dt is equal to P dV. And we know that for ideal gas for 1 mole PdV, Pv is equal to RT, where R is a constant. Differentiating both sides, we get P dV plus V dP is R dt. R is a constant, so dr is 0. Now for constant volume, this term is 0. Constant pressure, dP is 0. So P dV is equal to R dt. So this we can write Cp minus Cv dt is equal to R dt, or further I can write Cp minus Cv equal to R. So friends, this is how we can prove the Mayer's relation. Now after this, in the discussion, we will find that how do we find the specific heats of the of any gas, the what is the exact value of the Cp and Cv for different types of the gases, monatomic, diatomic and triatomic.